Hello everyone. In the last video, I discussed about Newton's backward and Newton's forward interpolation formulas. In today's video, I will discuss about the third important interpolation technique, which is Lagrange interpolation. So let us understand what is Lagrange interpolation and how it differs from Newton's backward and Newton forward methods. So first of all, this method does not require any difference table like in forward and backward Newton's interpolation. We need forward table and backward tables. So it does not require any table. And second important point is it works even when data points are not equally spaced, which is a requirement for the Newton's forward and backward. So even if the gaps between data points is unequal, we will apply this Lagrange interpolation formula. And third is very important. That means this Lagrange interpolation is little bit more computational for large data points. If I have 5 or 6 data points given at unequal gaps, then we will apply Lagrange, but it will be complicated at it directly generate the polynomial. So let us see what is the formula. So formula here is for any n plus 1 data points, let us call them x0, x1, x2, x3 and so on. You can write for x4, x5, x6. I am writing up to x3 only here and corresponding y values are y0, y1, y2, y3. Then using this interpolation, the polynomial can be approximated by this expression in the box y0 L0 x plus y1 L1x plus y2 L2x plus y3 L3x. If I have more terms here, then I have next term y4 L4x y5 L5x and so on. So we are restricted ourselves for x3 and y3 up to, and where these LIX, this means L0, L1, L2, L3, these are called the Lagrange factors. So which we need to compute for writing these polynomial. So Lagrange factors we need to compute. Let us understand how to write these Lagrange factors. So I need to compute first L0x. So L0x I will write as, because this is the corresponding for x0, this corresponding for x0. So in the numerator I will get a polynomial in terms of x, so I have to subtract every point except this x0 from x. So I have written here x minus x1, x minus x2, x minus x3. So except this x0, I have subtracted every data point from variable x. In the denominator will always give a pure number, no variable here, so it will be pure number. So in this denominator, you will subtract every other data point from x0. So I have subtracted here x0 minus x1, x0 minus x2, x0 minus x3. If I have next terms like x3 and y3, so here one more factor will be added in numerator, x minus x4, and in denominator x0 minus x4. So you can extend this. So let us write what is L2, so L1x. So L1x, I said it's corresponding for L1. So I have to write x minus x0, x minus x2, x minus x3. That means I have subtracted every point from variable x except this x1. And in denominator, we have to subtract every number from x1. So x1 minus x0, x1 minus x2, x1 minus x3. Similarly, you can write L2, which is for x2, So this I can write as x minus x0, x minus x1, and x minus x3 in numerator, and in denominator I have to subtract every point from x2. So x2 minus x0, x2 minus x1, and x2 minus x3. How to write L3, which corresponds to x3? So this can be written as x minus x0, then x minus x1, and x minus x2. In denominator, what you will do? You will subtract every data point from x3. So x3 minus x0, x3 minus x1, and x3 minus x2. We cannot subtract the same point from the x3 because it will result infinite or zero in the denominator and overall infinite. So we'll subtract only different number rather than itself. So as you can see here, in these factors, we have variable x here. So variable x, if I simplify these factors and put back into the formula, it will give you the polynomial, approximated polynomial directly. And suppose I want value at certain point here. Let's say I want value at xp here. The corresponding value I need to compute here. So for that, I need to calculate all these factors at x equal to xp. This xp can be anywhere in the beginning, in the middle part of the data point, or at the end of the data point. So we can write the polynomial by simplifying these factors in variable x. And if I need the value of x at any value of y at any particular x, we can directly compute these factors by putting x equal to xp here and x equal to xp here, x equal to xp here. And then we can get the numbers and then we can put in the formula. So I hope you understand the how to write these factors. So let's see one example here. So consider the following data points I have taken here. xi and y equal to fxi. So these data points are 1, 3, 4, 6, and corresponding y value is 2, 10, 22, and 70. So you can denote for your convenience. This is x0, this is x1, this is x2, and this is x3. And this is y, corresponding y values. So we have to compute y at x equal to 5. So x equal to 5 means xp equal to 5. So first of all, you have to check out in given problem whether the data points are equally spaced or unequally spaced. If you can see here, these one first is 1 and second is 3. So difference is 3 minus 1, that is 2. And if I go with x2 and x1, the difference is 4 minus 3, that is 1. So it is at unequal space between data points. So we use Lagrange interpolation. And we can write the Lagrange interpolation here. Let's make it A. So yx is the polynomial. It can be approximated by these y naught L0x, y1 L1x, y2 L2x, y3 L3x. And I have to compute these cofactors at x equal to 5. So I have written already this first factor L0, and you can see I have put the values. So x minus x1, that is 3, and x5 is x is 5 here. So 5 minus 4 and 5 minus 6. And then in denominator, we have to subtract the every value from x0, which is 1 here. So I have written here 1 minus 3, then 1 minus 4, then 1 minus 6. So ultimately it gives you 1 by 15. Similarly, you can compute the remaining And let's see these remaining factors. So I have now L1 x, so which we can write as x minus x0, x minus x2, and x minus x3, and divide by x1 minus x0 and x1 minus x2 and x1 minus x3. So this corresponds to x1, which is here 3. Now this implies what is L1 5. So this will be 5 minus x0, which is 1, and x1 is 3, x2 is 4, x3 is 6. So we can write x5 minus 1, and then 5 minus this is x2. So x2 here is 4, and 5 minus x3, which is 6. And in denominator, we can write here 3 minus 1, then 3 minus 4, and then 3 minus 6. And which will give you minus 2 by 3 on simplification. Now, third factor you can compute as L2x. You can write first the formula. So x minus x0, x minus x1, and x minus x3. We have to keep the sequence very clearly, otherwise it will be wrong. So this corresponds to x2 equal to 4. And in denominator, we will write here x2 minus x0, x2 minus x1, and x2 minus x3. So let us compute this. So I have here this factor as equal to 5 minus 1, then 5 minus x1, which is 3, and then 5 minus x3, which is 6. Divide by x2 minus all numbers. So x2 is 4. So 4 minus x0, that is 1, and 4 minus x1, that is 3, and 4 minus x3, which is 6. So on simplification, it will give minus 8 by minus 6, which is 4 by 3. Next, what I have, we compute for x3 equal to 6. So this factor is, here it is L2 5. So L3x first I will write as variable. So x minus x0, x minus x1, and x minus x2. Then x3 minus x0, x3 minus x1, and x3 minus x2. Now at x equal to 6, we can compute this. So this implies L3 at 5 will give you 5 minus 1, 5 minus 3, then I have 5 minus 4, and here I have 6 minus 1, 6 minus x1, that is 3, and 6 minus x2, which is 4. So this will give you 4 by 15 on simplifying. So now I have computed these factors, and they need to be kept in the formula, which is given as equation number A. So L05 is 1 by 15, L15 is minus 2 by 3, and L25 is 4 by 3, and L35 is 4 by 15. So now this means we can compute here. So this means using formula, we can approximate y at 5 now equal to L0, 5, and y0 plus L1, or better you can write y1 at L15 plus y2, L25 plus y3, L35. So this, the expression just put the values. So y0 here is 2. So 2 into 1 by 15 plus y1 is 10. So 10 into minus 2 by 3 plus y2 is 22, and L25 is 4 by 3. So into 4 by 3, and plus y3 is 70, and then L3 is 4 by 15. So on simplification, you can get 2 by 15 minus 20 by 3 and plus 88 by 3, and then plus uh, 280 divided by 15. So once you simplify this, what you will get? You will get here, it's 6 20 20 divided by 15, which is 41.47. So y at 5 is 41.47. Now you can verify also whether this approximation is correct or not at x equal to 5. So we can go from table and check out the previous and next values. So at x equal to 4, I have here 20 20 is 22. And at x equal to 6, I have here 70. So x is 5 is lying here. So we can we can initially guess the value at x equal to 5 should lie between 20 20 to 70. If your value is lying outside this range, this means you have done a mistake either in final calculation or in calculating Lagrange factors. So as I said, this is very computational even for the 4 5 data points. So be careful in calculation, particularly the sign and denominator values. So this is how we can imply the Lagrange interpolation formula. Now let us summarize the key points on three interpolation techniques, namely the Newton's forward, backward, and Lagrange interpolation. So these points are very, very important to differentiate the methods so that you can choose it wisely. So first one is these Newton's formulas are applicable for equally spaced data points. That means the gap between x values should be equal for between any two values. And if data points are not equally spaced, we have to go for Lagrange interpolation. Now, second point is while choosing, and it's very important actually. So we are choosing backward and forward interpolation depending on the location of the value of x for which I want to calculate functional value y. So if this xp is near the beginning of the data, we use generally forward formula. And if xp means the value for which I want functional value is near the end points, we use backward formula. Why we are choosing forward backward? Because if I have this xp near the beginning, So if I compute P here, so the gap between XP and minus X0, which is initial point, divide by step size, which is equal, so H. So this difference will be smaller. Your computation will be very easy. But suppose if I have this XP near the beginning and I am using backward formula, so this will be changed as XP minus XN, which is last data point, divided by H. So this gap will be large. XP minus XN, which is last point here, XN is last point. So this gap will be large. So your calculation will be lengthy. So this is the reason we are choosing backward or forward formula depending on the location of the value of X for which I need interpolate Y. Otherwise, if you apply any one, your answer will be same, means because both these formulas approximate the same polynomial, and for any n plus 1 points, the approximated polynomial is always unique. So whether you apply the forward or you whether apply the backward, it approximate the same polynomial. So difference here is only in the computational effort, not in the answer. For example, here I have solved this particular example in the previous video. If you have not seen, you can just go and watch out. So here I have applied for computing this 3 point y at 3.5. So you can see here this 3.5 is lying here. So ideally, if I use here, because the space between data points is equal between all, so we apply backward formula ideally. And this I have done in previous video, and we get the value of y, which was approximately, and remember this. So you can compute the value. But suppose if you want to calculate this value using forward formula, you can also compute and you can check out, you will get same value. Because both the methods will approximate the polynomial which fits this particular data as yx equal to x cube. So whether you apply backward or forward, it will not make difference in the value of y at 3.5. Difference will be only in computational effort. This point is very important. And the next point is the Lagrange interpolation rule. As I explained, it has Lagrange factors. So it is very computationally expensive because we have to compute Lagrange factors for every data point. So while dealing with Lagrange interpolation, be careful with the sign of the denominator part and particularly denominator values, because all values are uh, as a product of factors. So you have to be very careful for the sign of the values and denominator values. So let's summarize here again. First point is the Newton's forward and Newton's backward are used when data points are equally spaced. Newton's forward and backwards applicable for equally spaced data point. While Lagrange can be applied to unequal data points. So actually, More general method is Lagrange one because it is applicable for both the when data points are equally spaced or unequally spaced, you can always apply Lagrange interpolation formula. But the problem is when data is large in size or in the numbers. Suppose here in this example, I am taking here x values at unit digits. If these digits are given in thousands and y values are given in thousands, it will be difficult to compute Lagrange cofactors. So when your x values are large in tens or in thousand and y value is also correspondingly large because they approximate some polynomial, so it will be more large. So be careful when data points are larger, we have to be particular whether use backward or whether to use forward for equal space data points. And if data points is not equally spaced, we have only one option. We have to go for Lagrange interpolation formula. And while computing this, we have to be very careful about these cofactors. And I hope you understand how to write these cofactors easily. So just keep in mind, we are from given value, we have to just indicate from x0, x1, x2, x3, and so on. So here uh, it starts from 0, so 4 points are given. So I hope you understand the three interpolation techniques that are useful to calculate the functional value of the given data points between any mid value of data range. So if you have any doubts still on these three techniques, you can leave a comment. Definitely, I will try to answer your doubts. Thank you.